Okay, today we're going to look at some problems from 2.4 and 2.5 in our text, specifically focusing on derivatives of trig functions and the chain rule, so composite trig functions. Okay, so for the first three, we're just finding the derivative, the first derivative. So here we would have f prime. So the derivative of sine is cosine. So that's kind of our outer portion of the composite function. So we have the cosine of x squared plus x times the derivative of the inside portion of our composite. So the derivative of x squared plus x. So we would have the cosine of x squared plus x times 2x plus 1. And remember, this is the cosine of x squared plus x. This is the argument. We can never multiply into the argument. So to clean this up a little bit, we would write this as 2x plus 1 times the cosine of x squared plus x. So there's no confusion there. All right, so over here we have g prime of t. So here we have a composite of another composite. So we're going to have to use the chain rule a couple of times here. So starting with the outside tangent, so we would have secant squared of 5 minus the sine of 2t times the derivative of 5 minus the sine of 2t. Okay, so next, so we still have our secant squared. So now the derivative, we have 0 minus, derivative of sine again is cosine of 2t, times, now the derivative of 2t, which is 2. So we keep working our way in from tangent to the argument, which is 5 minus sine of 2t, and then the argument of our sine function, which is 2t. All right, so let's see, we have this expression times this, so this is negative 2 cosine of 2t. So for my purposes, I'm going to write this as negative 2 cosine 2t times the secant squared of 5 minus the sine of 2t. I think that cleans things up a little better. Okay, moving on down here. So this sometimes confuses people when they see the cosine to the fourth. So another way to look at this is the cosine of 3x squared plus 1, all of that raised to the fourth. So that's what that means when we see cosine to the fourth. Okay, so again, we're going to use the chain rule a couple of times here. So we start out with 4 times as if this was just like u to the fourth. So 4 times the cosine of 3x squared plus 1 to the third. And now we're going to work our way in. So then the derivative of cosine, which is minus sine of 3x squared plus 1. And then finally times the derivative of 3x squared plus 1, which is 6x. So again, cleaning this up a little bit. So we have a negative 6x times 4. So there's a negative 24x. Doesn't matter which one you put first. I will put the sine of 3x squared plus 1, and then I'm going to write this as cosine cubed of 3x squared plus 1. Okay, let me get another piece of paper here. We're going to move this one over because we're going to need a little bit more room for number 4. Okay, so again, we're covering problems from 2.4 and 2.5. So we're going to find y double prime, where y is equal to the secant of 3x. Okay, so again, we're going to start on the outside, which is secant, so y prime. The derivative of secant x is secant x tangent x. So we would have the secant of 3x tangent of 3x times now the derivative of 3x, which is 3. So again, we would have 3 secant 3x tangent 3x. Okay, so now to find the second derivative, we're going to have to do the product rule because we have the product of secant and tangent. So y double prime. So here's what I'll do to make sure that we keep track of everything. So we have the secant of 3x times the derivative of the tangent of 3x plus, and we would have tangent 3x times the derivative of the secant of 3x. So given the fact that with our secants and tangents, our derivatives with secant squared and then secant tangent, I think this may actually help us to write this out fully. Okay, so now we have secant 3x. So the derivative of tangent is secant squared. So we have secant squared 3x times, again, we're still using our chain rule, so times the derivative of 3x, which is 3, plus, then we have tangent 3x. So again, derivative of secant 3x, which we've already done. So we have secant 3x, tangent 3x, and again, times the derivative of 3x, which is 3. All right, so we got a lot there that we're going to simplify. Notice we have a 3 and a 3 in both terms, so I'm going to factor that out, and then with the 3 in front, that leaves us with 9. And so here we have secant cubed 3x, and then here we have tangent and tangent, so we have plus secant 3x, and then tangent squared 3x. Okay, so the only thing we could do, we could factor out a secant 3x and leave us with secant squared tangent squared. And it looks like a Pythagorean identity, but it's actually not. That tangent or trig identity would be tangent squared plus 1 equals secant squared. So you could factor out a secant, and that would look like this, 9 times the secant 3x, and then you're left with secant squared 3x plus tangent squared 3x. I'm not sure that that's a huge gain, but certainly one of the things that you could do in terms of simplifying. Okay, let's look at one more, a little bit of an application problem where we're finding the line's tangent and normal to the curve y equals 2 sine pi over 2x and x equals 1. Okay, so this is going to be an interesting one. We're going to find the equation of a line, right? We need a point. So x is 1. So when I plug 1 in for x, the sine of pi over 2 is 1. So we end up with the coordinate 1, 2. And now we need the slope. And that would be we can use the slope at 1 for the tangent line, and then we would need the negative reciprocal slope for the normal line. So to find the slope of the tangent line, we need the derivative. So derivative of sine is cosine pi over 2x times, and using our chain rule, the derivative of pi over 2x is pi over 2. Okay, so the 2's divide out, and we're left with pi times the cosine of pi over 2x. So now we want to find the slope at 1. So pi times the cosine of pi over 2 times 1. Well, the cosine of pi over 2 is 0. So that tells us that the slope is 0. So what we know is that if a line has a slope of 0, it is a horizontal line. So that means that, and again, this is a little bit about what your graph would look like. Right, there's your sine, but the period would be 2. So we get 2, or 4 rather, because the period, right, you would have 2 pi divided by the pi over 2, right, that's your b value. So your new period pi's would divide out, and 4. So there's 2, 3, 4, 1. So notice there at the top, right at where the sine curve turns, right, you would have a horizontal tangent line. And there's our amplitude, so that's 2. So for our tangent line, we would have y equals 2. And then for our normal line, which would be perpendicular, right, we would have a vertical line. And so the normal line would go through 1, so you would have the equation x equals 1. Right, so a little bit different. We don't always see that our tangent lines are horizontal, but there we get a slope of 0. And then when we look at our graph, that kind of confirms what we found. Hope that helps, and we'll see you soon.